Hi everyone and welcome to this new video about AC steady-state power. We continue with the maximum power transfer example. This is our example number 4. In this example we will consider a different situation. We will achieve a maximum power transfer using a transformer in this case. So there is a voltage source Vg given and the output impedance is modeled of this source by a series resistor and a capacitor, so a series RC circuit. There is also a model of the load, which is a series combination of the resistor and the inductor, R2 and L. The transformer is assumed to be ideal, and there are values for R1 and C and R2 given here, R1, R2 and C, and the voltage source is also given with a specific frequency of 1 megaradians per second. What is the question? This is the question. Calculate the turns ratio NP divided by NS and the inductance L to achieve maximum power transfer to the load. So there are two questions actually, the NP divided by NS, so this one, and the inductance. Okay, let's first write down what's meant by the maximum power transfer. So maximum power transfer, we know we need the source impedance, which is shown here, must be equal to the load impedance complex conjugate of that. In this case we have not a series combination of those two impedances, so how do we tackle this situation? Now what you should do in this diagram, in this circuit, is look at the reflected impedance. So that's actually the also important topic. So this impedance, looking actually in the primary side of your transformer, which is a reflected, I will define it with Z of L prime, which is a reflected impedance from the secondary side to the primary side. So I will first determine that equation or the expression for that, and this one, the complex conjugate of this one, must equal to the expression of the source impedance. So I will write it down in more detail here. So I will have the Z of S, which is a series combination of the R1 and the C, must be equal to the Z of L complex conjugate. Or we will say the complex conjugate of this one is exactly the same issue. So what is Z of S? Let's write it down. Z of S is equal to the R1 minus J of XC, which is just the series combination of the resistor and the capacitor. The ZL by itself is the series combination of the R2 and the inductor. And the ZL prime, which is the reflected impedance to the primary side, is this formula. You use the turns ratio of the transformer, you square that, and you multiply by the impedance which is seen at the secondary side. So this is actually a very important formula. And by taking the complex conjugate of the source impedance, this will become a positive, and you will express actually this expression with a positive sign to this expression. And of course the ZL is this. So let's move on by substituting those values. So R1 plus JXC must be equal to M pi divided by MP divided by NS quantity squared times, and the ZL can be written as R2 plus J of XL. So what you can see is we have actually the unknowns already in this expression. This is one of the unknowns actually in the calculations, and this is also the unknown here because the inductance is actually hidden in this expression. So this omega times L. So let's fill in what we have. We have the following. The R1 is 20, so let's continue with black. So this is 20. I don't know X of C. I can calculate this. Let me do that next. So X of C is equal to 1 over omega times C. So I have the omega, which is 10 to the power 6. I have also the capacitor value. This is 100 nanovarads. That means actually 10 to the power minus 7. 10 to the power minus 7. In scientific notation, this will be 10 ohms. That's actually for this situation. So what I have is the following: J 10, so 20 plus J10 is equal to ratio NP divided by NS squared, still unknown. I know R2, which is 180, plus J and an omega, of course, because this is also true. XL is equal to omega times L, which is 10 to the power 6 times L. Still one unknown, but it's actually the unknown we want to determine. So take 10 to the power 6 times L. What you can see is two unknowns, actually, and two left and right. You have actually the real part and an imaginary part. So what we do is very simple. You equate the real part of the left side to the real part of the right side, and you equate the imaginary part of the left side to the imaginary part of the right side. So I will do that. I will have the following. Let me continue with blue. The 20 must be equal to NP divided by NS squared times 180, and these two conditions must hold. So 10 must be equal also to NP divided by NS squared times 10 to the power 6 times L. Now, I have two unknowns in this expression, so it is better to start with this one because I already have the ratio here. So what is the ratio? NP divided by NS squared will be 20 divided by 180. This will be, we will get so let me write it down. So 180, this will be 1 over 9, so 1/9. So if I take the square root of that, I will have 1/3. So this is the 1 over 3. Okay, I already have the expression for NP divided by NS. I can now substitute this expression here, or use this expression as 1 over 9 here. So what do I have? It's next. So actually, I am almost done. So 10 is equal to 1 over 3 squared times 10 to the power 6 times L. I have 10 is equal to 10 to the power 6 divided by 9 times L. If you do the math, you will get 9 times 10 to the power minus 5 henries. That will be 90 micro henries. So I have the NS of NP divided by NS, and I have also the inductance, the inductor value L, and those are two unknowns in this example. And we are actually very easily we came very easily to the expression by using actually the formula, the definition for the maximum power transfer, and equated the real parts and the imaginary parts. That's actually very important. But the very important point here is don't equate this expression to this expression because we have a transformer in between. So you have to also use that effect such that this whole circuit will become one circuit. So what you actually have using the reflected circuit, I will make the drawing here. So using the reflected circuit, you will get the following. You will have the voltage source, VG, and you have the R1, C, and your reflected impedance will be in series, and this is actually the model of this circuit completely. This circuit can be modeled in this circuit because this one is reflected impedance from the secondary to the primary side of the transformer, and that's actually the whole exercise example about maximum power transfer. So you will have a maximum power transfer using the ratio of NP divided by NS of 1 over 3 and the inductor value of 90 micro henries. Alright, that's for example number 4, and I see you next time, and have a nice day.